So today we want to get to the Maxwell relationships, but first just a reminder of the Gibbs free energy, which we defined in a previous lecture. It's a definition of convenience, and it is a group of thermodynamic variables, all of them state variables. The change in Gibbs free energy gives us the maximum possible shaft work that we can obtain from a closed system, not in motion, under constant pressure and isothermal conditions, by setting SP equal to 0 and combining the energy balance and the entropy balance for that system. If we apply the energy and the entropy balance for the same system, but with shaft work equal to 0, we get to the important result that the change in Gibbs free energy of that system is equal to negative SP times temperature. That implies that a change in Gibbs free energy for a closed system not in motion under these conditions must always be less than or equal to 0. This is a seriously important result that we are going to use again in future lectures. But for now, we only use our definition to generate our final fundamental equation. And to do this, we realize that since this is a group of state variables, if we want to calculate the change in Gibbs free energy, we can design our own path, change the enthalpy, keep the temperature constant at temperature 1, for instance, and change the entropy. Now we keep the entropy constant at the second value or the endpoint value and change the temperature. We can only do that because the path doesn't matter in the case of state variables. Now we recall one of our first fundamental equations that you've been using in your entropy calculations for the ideal gas, and substitute dH in there, and we have derived our third fundamental equation. For our final fundamental equation, we use another definition of convenience, which is the Helmholtz free energy. It's equal to the internal energy minus the temperature times the entropy. And it was derived by considering a system similar to the previous one, but in this case the volume was kept constant, still isothermal, still closed, and not in motion. And poor Helmholtz, we have to use the variable A because of H, of course, was already taken for entropy. This is from the German word for Arbeit. And again, we could prove, if we go through the energy balance and the entropy balance, that if we combine the two, since we want to write Q in terms of thermodynamic variables of entropy and temperature from the entropy balance, that if SP is set equal to 0, Q substituted in terms of entropy variables, we can prove that the maximum amount of shaft work from such a system can be given by the change in the combination of those variables, or the Helmholtz free energy. Also, if the shaft work is now set equal to 0 in our energy balance, we can prove that if we now do not set SP equal to 0, this is equal to minus temperature times entropy produced, and it must be less than 0. In this case, the temperature and the volume of the system is kept constant.